All right. So if you want to highlight this box, that's the remainder theorem. You can. Right? So when a polynomial is divided by a binomial x minus a, then the remainder is p of a. And, well, they've got it. Yeah, you've got an example right above. I'll pull up that example. So they put this example here, okay? And the key thing for us to see from this example is that if I write out the division statement, the dq plus r, I would have 5x cubed minus 2x squared plus 8x minus 1 is equal to x minus 2 times by 5x squared plus 8x plus 24, and the remainder was plus 47. When I plug in 2 into this side of the equation, I will get 47. And the reason I get the same as the remainder, because plugging in 2 on this side of the equation has to be the same as plugging in 2 on this side of the equation. And if I plug in 2 on this side of the equation, what's that part in the box going to equal? 0. And 0 times anything is going to be 0, and all you're going to be left with is your remainder.
So do you always plug in a positive number? Like even if it's x minus 2, you just plug in?
Well, x minus 2, you'd plug in positive 2. If it was x plus 2, you'd plug in negative 2. You're always plugging in the number that in that box would make it equal to 0, because then all you would be left with is your remainder. And so this is called the remainder theorem. And it's based on this idea of whenever you substitute it into your division statement, you're going to get 0, so all you're left with is your remainder. So let's look at example number 1. Determine the remainder when 2x to the 4 minus 5x cubed minus 5x squared plus 5x plus 3 is divided by each. So now you have 2 options to find the remainder. Option number 1 is the remainder theorem. Option number 2 is do synthetic division, and whatever numbers at the end will be your remainder. Okay? We'll do both, and you can decide which one you like better in each case. The theorem will always work. So if I plug in, if I let p of x equal this, so I have to define p of x so that I can use this notation, then p of 3 would equal 2 times 3 to the 4 minus 5 times 3 cubed minus 5 times 3 squared plus 5 times 3 plus 3. Okay, 162 minus 135, that's an ugly 5. Minus 45 plus 15 plus 3. Mental math, 0. Okay? How was that for mental math? Not good? What were some of the hard things? 3 to the 4? 81? That's one of the hard things? 81 times 2? This would be on non-calculator. The 3 cubed, 27 times 5? How's that one? That a little bit hard, mental math-wise? Okay, this is the remainder theorem. With the 3 in there, the mental math is a little bit challenging at times. And then you have to add all these together. Okay, I kind of cheated. I put the negative ones together and saw that was negative 180. I put the positive ones together. 18 plus 162 is positive 180. And then I did 180 minus 180. 0. Yeah. Okay. With synthetic division, this looks like this. The coefficients are already in the right order. 2, -5, -5, +5, +3. We're dividing by x minus 3, so I'd put a +3 outside. And the synthetic division would look like this. Bring the 2 down, multiply, add, multiply, add, multiply. Oops, don't make a mistake. There we go. -6, -1, -3, 0. There's my remainder of 0. Synthetic division in this example, I think, is nicer, right? Whereas the highest number we had to multiply in this whole thing was 3 times 2. Or I guess 3 times -2 was probably even harder. That was the biggest multiplication we had to do. Whereas in the remainder theorem, you had to do 27 times 5. That's a little bit more difficult multiplication than 3 times 2. Okay? In synthetic division, the biggest numbers you ever had to add were 5 plus -6. Okay, that's the biggest numbers you ever had to add. In the remainder theorem, you had to add 162 minus 35 minus 135. The numbers for adding were bigger as well. The remainder theorem is really nice if you're plugging in 1 or -1, because then it's really quick, because adding and subtracting isn't hard. But anytime you go bigger than 1 or -1, the remainder theorem is sometimes annoying. Okay? No, but on an exam, it will give you a part of a question where they tell you part of the remainder theorem, so you have to use that method over synthetic division or something like that. So you still need to know them both. Okay? I'd like you to quickly do the -2 with both the remainder theorem and synthetic division. I'll do it as well so that you can check your answer once you're done. Interesting. We got the same remainder, 45 both times. If you didn't get 45, something went wrong with the mental math somewhere. And this time, maybe the numbers with the remainder theorem were better, right? Because the biggest thing I had to multiply in my remainder theorem was 16 times 2 or 5 times 8. Not so bad. But the biggest thing I needed to multiply in my synthetic division was 2 times 21. So in this case, it seems like they're about equal. So as the numbers get closer to 1, like 1 and 2, sometimes the remainder theorem is just as easy as synthetic division. The nice thing about synthetic division, because eventually we're going to be asked, can you factor this? The nice thing about synthetic division is when you get a remainder of 0, which we did here, we now know that our original polynomial p of x is equal to x minus 3 multiplied by 2x cubed plus x squared minus 2x minus 1. And we've started to factor it. So the synthetic division not only tells you the remainder, but also tells you what the answer to factoring it is if you write the division statement. Yes?
What is negative 2 to the 4? Like, is it like 2 times, yeah, is it 16?
Positive 16. So negative 4 times will be positive, and 2 times 2 is 4, times 2 is 8, times 2 is 16.
Why is this working? Because I, like, do you count 2 times 2, and then 2 times 4, and then 2 times...
Okay, questions for practice are 4a, 6a, 7, and 8. And we're going to do example 2 right away before we start these.